Alright, I'm back with another intro video. This is for MIT's 2155-2156, demo 9 of fall 24. And this demo is basically expanding upon the challenge problem. We're giving you a solution to the challenge problem using diffusion models. So we've given you essentially a trained diffusion model called bike fusion. And at the very beginning of the notebook, we're going to be, first of all, importing the challenge problem 3 code as well as the bike fusion model. So this bike fusion repository basically has some other functions related to the diffusion as well as the model itself. Alright, so quick background on diffusion models. Basically what we're trying to do is learn a mapping from pure noise to generated data. This is the premise. And basically we're going to start off the notebook with a lot of the same stuff as in the Challenge Problem 3 notebook. And by the way, if you haven't gone through the Challenge Problem 3 notebook, I recommend you do that first before watching this video, or take a look at the video I posted recently on Challenge Problem 3. But anyways, we're going to load up the data. This is the same stuff as in the other notebook. And in addition, we also give you essentially the indices of the training and validation splits that we use to train the bike fusion model. All right, so this is useful if you want to use the pre-trained bike fusion model, do something with it, and when you want to basically do cross-validation, evaluate how well whatever your solution is working, you probably want to evaluate the designs that were not used in the training data for the diffusion model, so you can figure out which ones those are, figure out what the validation split is, using val indices and train indices, which we provide here. So that can be useful for various reasons. Okay, so the first thing we're going to do is, reuse this mask function that I just grabbed from the CP3 notebook. And basically what this is doing is creating a channel of masks. I explained this in the other video. So we included a little visualization here just because the masks are a little bit more important here, understanding exactly what's going on. But basically this is like black in the regions that are not masked out, and then white in the region of the mask. Okay? So one thing to note is that for the diffusion model, the bike fusion diffusion model, the pre-processing is a little bit different from what we did in the starter notebook. So this is important because if you were to run the pre-processing in the starter notebook and then try to apply, feed that data into the diffusion model, it wouldn't really work out. So the main differences here are that we have padded the images to be 128 by 128 instead of the original 80 by 128. We've done this to basically use standard off-the-shelf UNet models more easily. So UNet models are just easier when they're working on square images. So we've just added some extra white bars basically to the top and bottom. And yeah, maybe it's a little bit wasteful, but we determined it was worthwhile so that we could use powerful off-the-shelf standard architectures and so forth. Okay, so that's one difference, is this padding. And the other difference is that instead of scaling from 0 to 1, we're actually scaling from -1 to 1 here. And the reason is that it's just easier dealing with like diffusion and noise if the noise is centered around 0. So this is kind of just to make our lives easier. Okay, so we can take a look at the pre-processing here. So this bike fusion.preprocess applies the pre-processing, and we can see after the pre-processing, the shape of the images is 128 by 128, and the range is -1 to 1. All right. And we also provide this post-processing, which basically turns the processed images back into the normal. So the remapped images will be 80 by 128, and you can see 0 to 255 for the range of values. Okay, so just be mindful that this pre-processing and post-processing is different from the processing that was applied in the starter notebook for that VAE. Okay, so let's see. So some more visualization. We can see, okay, this is like the original, this is the pre-processed and the post-processed. There's a little bit of change in color here. I think this is just a matplotlib thing when it's dealing with different data types, but it's basically the same. All right, so next up, we're actually going to load the diffusion model here. So we've given you a function, load bike fusion, that loads the bike fusion model. This model is now called diffuser. And first of all, we just take a look at the architecture of the model. So you can see this is a very, very big and sort of complicated model. There's a lot of, so there's like, it's a UNet basically, and there's convolution layers. There's a lot of attention blocks actually, and so this is using attention. And in total, we have 170 million parameters. So compared to I think the VAE that we gave you in the starter notebook was like 700,000 or something like that. So this is like 200 times bigger. So this is a big model. This is why we've pre-trained it for you. It's because training this is no joke. So we've done the training, and hopefully you don't need to do any training, but we will give you the training code in case you want to try to train a better version. Okay, so basically over here we're just taking a look at the noising process to make sure that everything looks good. We can see that basically we're gradually adding noise as we expect. And over here now we're doing unconditional generation. All right, so we're saying diffuser, that was what we called our model. Diffuser.generate, this is the function we've given you to basically generate new samples. Okay, so we say 6 samples, return intermediates is true. This is so that we can see all the intermediate steps here, and then num inference steps is 10. So we're just using 10 inference steps so that we can sort of visualize them, and it's a little bit faster. But in practice, if you used more inference steps, the quality of the images would be a lot higher. All right, so 50 to 100 inference steps would yield better results. So this just took 13 seconds to generate. So if you did more inference steps, it would be slower. Okay, so this is what it generates with 10 inference steps, and you can see that these images actually look pretty realistic, right? So these are actually generated bike images, and you can see they look pretty similar to what you might find in the data set. Now, one thing that's notable is that there is some color shift over here, and this is actually pretty common in diffusion models, but we'll see later on in the notebook how this can be pretty easily solved with some guidance, or there are other ways to fix these issues as well. So pretty realistic looking samples. Again, this is unconditional generation, right? So going from noise to any sample, we're not trying to reconstruct a specific one. And this is what we end up with. Okay, so not bad. Next, we want to do conditional generation. So the idea is that, okay, maybe with a masked image, we would like to generate the remaining components, basically as is the challenge in CP3. Now, the way that we've trained this diffusion model, actually, we have basically trained it both using masked images and using just like freeform generate anything. So the way that we've done this is we have basically given it a mixture of masked images and just empty blank slates as conditioning information. All right, so the conditioning information is 3 channels. If it's a masked image, it'll try to use this knowledge of the unmasked portions to try to match. And if we just give it like a blank slate, we basically say the entire thing is masked out, it'll generate whatever it wants. That's the idea. So by training it with this mixture of blank slates and masked images, now it's essentially learned how to do conditional generation and unconditional generation, right? So the syntax here is that we have this function getSampleBatch. This will give you a batch of 10 validation data points, and this gives you the mask samples, the actual masks themselves, and the images. And we've also given you this nice function here to visualize this. So this is just taking a look at this data that we've grabbed from this getSampleBatch. Okay. Next, we're actually going to call the model on the mask samples, the sample masks, and the image samples. So here we grab 8 new ones. It's going to be the same type of thing as this. And let's see. So before this, actually, we specified that. Oops. Okay, this is going to run again. That's going to take a minute. We specified that we want the probability of getting a full image to be 0. So this getSampleBatch, actually, once we've set this parameter to 0, it's actually going to give us a batch of only masked samples. And then we reset this back to default over here. So this parameter here, this full image probability, will impact what types of samples you get out of this getSampleBatch thing. It's unfortunate this is running again, but I'll scroll down so you can take a look at some of these results. I think this is the same thing down here. Basically, this is what we end up with. These are our masked images. This is what it reconstructs. You can see there's still some color, color shift issues, but in a lot of cases, it's coming up with bikes that are, pretty reasonable given what we masked out. Okay. So this is what it comes up with. Let's see if this is done up here. Not quite. So what I did here was we have a couple cells, and we wanted to evaluate the scores using the CP3 scoring function. And this function here is reused from the CP3 starter notebook, which basically combines the prediction with the known unmasked portions, right? So we only care about the prediction inside the masked region. So basically we're combining the prediction inside the mask with the known portions outside of the mask and evaluating scores here. If you remember from the starter notebook, I think the VAE that we gave you is scoring around 0.95. So this model, although it generates very realistic looking stuff, it's actually scoring worse than the VAE that just gave very, like, wishy-washy stuff. And part of that is that, this is generating realistic looking stuff, but it's guessing, and sometimes it gets it pretty wrong, and this is penalized in the score. So another thing to keep in mind is that, this is finished running again. So the reason why I ran this twice is because I wanted to show, for these exact same masks, unfortunately, I have to run this next one again. So, yeah, originally this was showing how for the exact same set of masks, if we call the model 2 times, it gives very different outputs. And I think if you run this from the top, you'll probably see that. So the idea is that, the diffusion model is very diverse in what it generates, even for the exact same condition. And yeah, there's another example where you compare two side by side further down in the notebook with guidance. So hopefully that'll show over there. And accordingly, the scores are also very different every time you run it, right? So it'll sometimes generate something that looks like this, and then sometimes it might generate a bike that looks much more closer to the target. So it'll have different scores every single time you run it. If you do a lot of aggregation, you average over a big batch, it'll probably be similar, but I would think about how you can leverage the diversity and the variability of what it generates to your advantage, right? So you might be able to do some kind of select the best out of many different options that it generates, right? Okay, so this is the this is the conditional generation, right? So we give it, this mask, and this is what it generates. Now, there are other ways to do this in-painting task without using conditioning. So with the conditioning, we had to specify at the beginning, when we train the model, we're going to pass it this mixture, again, over here, this mixture of masked and totally, blank slate conditions. And this is exactly what we've done for this conditional model. But if we wanted to, condition it with something else, we would have to totally retrain the model. But there are ways to control generative diffusion models using something called guidance that doesn't require retraining, which is really neat. So what this does is it takes just an already trained diffusion model, and as it's basically predicting all the denoising steps, it's going to apply a push basically to try to steer it to something else. So in this case, we are actually going to demonstrate how we can do unconditional generation, but just basically push the model as it's denoising to get it to learn the in-painting. So the way that we do this is we set up a guidance function. And in this case, the guidance function that we set up is basically going to look at the error between what it's predicting and the regions that we know, right? So if its prediction for the final output is very different from, the regions of the bike that are unmasked, then this error is going to be very high. Okay, so the specific way that we set this up is we say, okay, we're going to take its prediction, which is these denoised images, and we're going to basically apply this white masked box in the same position that we see in the mask. And then we're going to compare this guy against the ground truth and calculate the error of that. So basically any regions, because these white boxes are in the same spot, so there's no error between them, but everywhere else, wherever it's different, we're going to be assigning some error. So this is our function here, and this is minimized at 0 when we have a perfect match in all of the unmasked, or all of the unmasked regions. And this will be very high if we're not being consistent in matching our mask. And we actually can just pass this into our diffusion model here. We say guidance function equals sample guidance. And also notice that we're not passing in any conditional information. Up here, the conditioning was passed in over here, right? So torch.tensor of masked samples. This was passing in a condition. In this case, we're calling generate without passing in any condition here, right? There's nothing in the way of condition. So we're doing unconditional generation with guidance using this sample guidance function that we've created. And what ends up happening here is that we can also basically do this in painting. And actually, what's nice about it is that this guidance has actually fixed the color jitter, because in forcing it to try to be consistent with all these unmasked regions, it basically sees, oh, I need to try to match this color to the pure white color of the unmasked regions. Okay? So, obviously this is still not perfect, but we can see that this guidance mechanism works pretty well in terms of enforcing that what it generates are consistent with the unmasked regions. Okay? And again, what's really cool about it is that we're taking this pre-trained, fixed model. We're not we don't need to do any training. We can apply different types of guidance, whatever we want, and this will just apply during inference. So it's very flexible. So, and then over here, because I didn't rerun the cell accidentally, we can compare this output with, oh, for some reason it's not showing this. I just encourage you to try this yourself. Basically, run it, visualize one set of outputs that it generates, and then compare that to another set of outputs that's generated for the exact same set of masks. And you'll see that oftentimes it actually generates some different stuff. Okay, so in terms of scores, this is hitting 0.955 or 0.954, and this is over 2 runs. And yeah, I mean, this is maybe slightly better than the VAE model, but again, I think to get a lot of improvements, you're going to have to figure out how to incorporate some knowledge from the text or the parametric data, because otherwise, at the end of the day, it really still is just guessing what's inside the box. Okay, so in terms of reflection questions, we've basically asked you to do 2 things, and 2155 students will do one of the 2, and 2156 students will do both. Okay, so one of them is basically combining the guidance with the conditioning, right? So in this example here, we gave you guidance without conditioning, and in this example up here, we gave you conditioning without guidance, but you can actually pretty easily combine the 2. So you can see how we passed in conditioning here. This is the condition information, and then over here we passed in guidance, right? So this is the guidance function. You can try combining the 2 and see what it does. And ideally, it should learn this mechanism through both the conditioning and the guidance to try to enforce the unmasked regions in this in-painting task. By the way, something I forgot to mention, this guidance scale impacts basically the magnitude of this push that we give it. So you can change this guidance scale to modulate the impact of this guidance term during the denoising. Okay, so that's the first assignment. This is, where did it go? Yeah, so implementation of hybrid guidance conditioning. The other option is to implement a custom guidance function. I think this is really interesting. So as I mentioned, this guidance function can be anything as long as it's differentiable. So you could basically ask it to do some very different things. Like you could apply some guidance specifically to do some kind of color shift, or there's a lot of different options. So basically the other option is to basically make your own custom guidance function. And just remember, it has to be differentiable, but that still leaves you a lot of options. Okay, so 2155 does one of these 2 things, and 2156 we expect to do both. Now, hopefully this is something that you can easily see how to apply this to the challenge problem. The goal is that we would make your lives easier by basically having Demo 9 directly feed into the challenge problem. Yeah, you're welcome to exactly use this bike fusion model that we gave you. We've provided it specifically for your use in the challenge problem if you'd like. And yeah, there's a lot of opportunity to do custom guidance, do some kind of subsampling if you generate many samples and figure out which one of those maybe match the text prompt most closely. There's a lot of different ways to leverage the diffusion model. All right. Yeah, I think that's it. As always, come to office hours or message us if there are any questions, or post in the discussion channel. And yeah, looking forward to what you all come up with. Good luck.